In the previous block, we discussed that we can excite electrons and holes by the absorption of light. However, holes and electrons also suffer from loss mechanisms. If an excited electron and hole meet each other, they are able to recombine. They join each other and lose their mobile state, or in other words, the electron is glued again to the background in a molecular orbital. Or in other words, it is the annihilation of free charge carriers. First, we will then identify three different recombination processes, and we will conceptualize the underlying mechanism of each recombination process. There are three different recombination processes: radiative recombination, Auger recombination, and Shockley-Rittal recombination. Let's start with radiative recombination. In radiative recombination, the energy of the electron is emitted as a photon after recombination. The energy of this photon is the same as the band gap of the semiconductor material. Radiative recombination is, in fact, the mechanism that light-emitting diodes or LEDs utilize. Radiative recombination is very significant in direct bandgap semiconductors, but relatively rare in indirect bandgap semiconductors like crystalline silicon. Next week we will discuss this in more detail. The next process through which excited charge carriers can recombine is Auger recombination. Auger recombination is a three-particle process. The momentum and energy of the recombining hole and electron are transferred to another electron or hole. This third particle is excited deeper into the respective band, making the electron or hole hotter, and then relaxes again by a process called thermalization. In this thermalization process, this free electron, in essence, loses some of its energy in interactions with the crystal lattice. Auger recombination strongly depends on the charge carrier density, since a higher concentration increases the probability that these three carriers can interact in this way. The third recombination mechanism is Shockley-Rittal recombination. Semiconductor materials can have various types of defects in the lattice. These defects can have energy states in the forbidden bandgap, like we have seen for donor and acceptor states in the case of doping. An electron can be trapped in such defect states. If then freely moving around holes can find these trapped electrons, they can recombine as well. It can happen the other way around as well. A hole can be trapped in such defect states. If then freely moving around electrons can find these trapped holes, they recombine as well. The loss mechanism, like recombination, determines the lifetime of the charge carriers. If the recombination rate is high, the lifetime of charge carriers is low. The average distance the excited charge carriers can move around is determined by the lifetime of the charge carriers. This average distance is called the diffusion length. If the recombination rate is high, the diffusion length will be shorter. When the recombination rate is low, the diffusion length will be longer. The diffusion length and the lifetime are related with a relatively simple equation. L is the square root of the product of d and tau, where L is the diffusion length, d is the diffusion coefficient, and tau is the lifetime. Let's consider now a p-doped semiconductor material. The holes are the majority charge carriers and the electrons are the minority charge carriers. The holes have a small probability that they will meet an electron, and therefore the recombination rate is small. On the other hand, the electrons have a high probability to meet one of the holes, as the hole density is many orders of magnitude higher. This means that the recombination rate for electrons is high, or in other words, the diffusion length of the electrons is short. Let's now consider n-doped semiconductor material. The electrons are the majority charge carrier and the holes are the minority charge carriers. The electrons have a small probability that they will meet a hole, and therefore the recombination rate is small. On the other hand, the holes have a high probability to meet one of the electrons, as the electron density is many orders of magnitude higher. This means that the recombination rate for the electrons is high, or in other words, the diffusion length of the electrons is short. Important to remember is that in a doped material, the minority charge carriers have a short diffusion length in reference to the majority charge carriers. So now, we know how to excite charge carriers, we know how to manipulate the semiconductor material to create majority and minority charge carriers, and we understand the transport mechanism of charge carriers. It is time to build a solar cell. We will do that in the next video.